Slide 3 shows a picture of a regular LTA with 2 time points, and we're going to consider binary indicators U1 through U12 here. So we have 2 latent class variables, C1 and C2, and we're interested in the influence of C1 on C2, also referred to as a transition. So the parameters in this model are number 1, indicator probabilities for each indicator U, where we have a probability for the indicator J referring to the number U1 in this case, conditional on class at a certain time point, CT. That is, the probability of this being 1 instead of 0 for class 1 and for class 2, etc. So those probabilities are showing the strength of relationship between the class and the indicator. And we in Mplus parameterize that as a threshold. Second, we have initial status probabilities, the probabilities of C1 here at the first time point. And then third, we have transition probabilities, that is probabilities of C2 classes given that we are in a certain C1 class. Now the indicators here can be of many different kinds: continuous, binary as we just talked about, ordered categorical, that is ordinal, or unordered categorical, that is nominal, or counts, or any combination of those. Now here we can also include covariates X in this picture, influencing C1 and C2, and study how covariates influence not only the initial status probabilities but also the transition probabilities. And we talk about that in Webtalk 2 on slides 58 to 64, where we also distinguish between effects of covariates on this transition that are main effects or interaction effects. So the main effect is that X influences C1 and influences C2. The interaction effect is that we have a C1 specific effect of X on C2. A C1 class specific effect of X on C2. Now for a discussion of regular LTA, I refer to Mplus Webtalk 2, where this is described in detail. On slide 4 then we have the input for Mplus analysis of a regular LTA. And we have this generated data set. At the end of the talk I show the input for how this data set was generated. So simulated data for a sample size of 2,000, indicating that with the LTA we do want to have larger sample sizes than we do typically for LCA. And we get an entropy measurement quality for both C1 and for C2 of a moderate level. Here are the names in the data set, and the variables that we're going to use are U1 through U12 here, and with this missing data flag. And we are going to specify 3 classes in each of the 2 latent class variables. And we declare U1 through U12 as categorical, and the program figures out that they are in fact binary. And we do mixture modeling with a moderate level of starts, 40 initial and 10 final analysis based on these perturbed random starting values. With LTA you may want to, in general, increase that, maybe double it to 80-20. Slide 5 shows the input for regular latent transition analysis modeling part. And the modeling part has 3 pieces to it. One is the overall, the other is model C1, and the third one is model C2. So in the overall part here then we say C2 regressed on C1. And that statement also produces several things. First of all, it produces the regression slopes C2 sharp 1 class number 1 on C1 class number 1, C2 class 2 on C1 class 2, and etc. for the second row of C1, namely C2 number class 1 on C1 class 2, C2 class 2 on C1 class 2. So the first and the second row of the regressions. That's what C2 on C1 implies, but it also implies these values for C1 and C2. So C1 class 1 and C1 class 2, those are the initial status logits producing the initial status probabilities. C2 class 1, C2 class 2, they produce the intercepts in the regression of C2 on C1. You can explicitly say these things in the model. You would have to put brackets around them because they are level related parameters. This is a mean, this is an intercept to talk in continuous variable terms, and here are the 4 slopes. You see this discussed in detail in Webtalk 2, but also at the end of chapter 14 of the user's guide, which describes the logit parameterization. But Webtalk 2 gives more detail to it. So that's the first part, conveniently summarized in this statement, but you should be aware that it produces 4 slopes and a couple of means and a couple of intercepts. Now, model C1 then has the thresholds for the 6 latent class indicators at each of the 3 C1 classes. So that refers then to the first part of the modeling parameters that we showed in the picture, whereas the other parts are in the initial status and the transition parts of the model. Model C2 then, well, we repeat the same structure here, but we start then with U7, the second time indicators, 7 through 12, for each of the 3 classes. And we're going to use equality constraints. You see that first class 1 through 6, first class 1 through 6, same parameter values. We hold them equal across time. Because we're thinking about this, and the same for the other classes. And we're thinking about this as a typical LTA application, where U7 through U12 are the same measures as U1 through U6. Same measures, same variables, but recorded at time 2. And to make sure that we capture the same latent class construct at the 2 time points, we want to specify measurement invariance across time by these equality constraints expressed by these parameter labels that we have given here. Now, it may not hold exactly perfectly, and you may want to look for deviation from that full measurement invariance, and I discussed that in Webtalk 2. But that may well be your baseline assumption that you would start out with. On slide 6, we see a very useful piece of output that gives latent class indicator probabilities. Here we give them for C1, it's the same for C2. Same probabilities for the 2 time points due to the measurement invariance that we specified. So you have the 6 indicators here. In this case it's U1 through U6 because we're talking about C1, but it's the same for U7 through U12. You have the 3 latent classes as columns, and we look at the highest category, which is U1 equals 1 as opposed to 0, but we number the categories as 1 and 2. And you see then that class 1 consists of people who have a high probability of saying that they do whatever U1 involves. High probability of U1 equals 1 for all the U's. So that's the high class. Second class is low, 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 high, high, high. So it's a low, high class. And the third class is a low, 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 low. Low for all items. And in this case, class 3 turns out to be the most frequent. So that's the normative class, having a low probability of engaging in whatever behavior the use refer to. So slide 7 then gives the latent transition results. We have first of all the latent class probabilities for the starting point at time 1 and for time 2. The latent transition probabilities based on the estimated model is what we're primarily focused on here. So the rows are the 3 classes of C1 and the columns the 3 classes of C2. So for people who start in C1 class number 1, that is being in the first row, they have a probability of 0.483 to stay in class 1 at time point 2, and lower probabilities to move to other classes at time point 2. Same thing for class 2, where the probability is the highest to move to class 3. Typically we have higher values on the diagonal. Some kind of inertia is often seen, and that's seen for the third row, where the highest probability is staying in class 3. What we want to do here is look at this in another metric as well, transition probability odds. So at the bottom here of the slide, you have a table where the diagonal has 1. So what we're doing is we're looking at the odds of moving to another class at time 2 versus staying in the class that you began at. So we're comparing to staying in the same class. So the value 0.474 here is simply obtained as 0.229 divided by 0.483. So we're comparing probabilities in an odds metric, so a ratio of probabilities. And we see that that's less than 1. And we can look at the confidence interval, which takes into account non-symmetry, as it should. And so it's a non-symmetric confidence interval. And it does not include 1, which says that 0.474, that odds, is significantly less than 1. So it's significantly less than the 1 odds here, which says essentially that the probability of moving to class 2, 0.229, is significantly lower than 0.483 in the odds metric. The odds for the moving to class 3 versus staying in class 1 is a little bit higher, because that probability is a little bit higher. So the key question is if the confidence interval includes 1, making it insignificant, versus not including 1. And the odds can be either smaller than 1 or greater than 1. With x's included in the model, we also have transition probability odds ratios, because then we're talking about 2 variables. Odds refer to 1 variable, C2 for being in class 2 versus class 1, but with an x variable we have 2 variables, and we can see the effect on the transition probabilities in terms of odds ratios as a function of each of the x variables. So that's not available or not used here because we don't have any covariates.